To understand the process of a Thevenin equivalent, I want to do this Thevenin equivalent example. To prepare a circuit one removes a load and creates an open at nodes AB. So our circuit looks like this. So now let me add the values, which is 6 ohm, 12 ohms, 3, 10, and then our load is going to be right here. So now one removes the load. So when you remove the load, if I just copy the circuit and place it over here, this is what the circuit looks like after we remove the load. So our goal is to replace, let me be careful here. I did not do a good job. So if I look at our circuit here, the goal is to replace this circuit with the equivalent. Where now we have a single source and a single resistor between nodes A and B, where this now is RTH and this is VTH. Once again, we have to be careful here. So when I draw it like this, everything is from the point of view of the load. And I need to keep repeating that because the circuits are physically not the same, but from the point of view of the load, they are the same. So now I have my circuit. So this is the circuit that I'm going to deal with, and I'm going to copy this. I think I already have it. And I want to deal with the circuit here. So here we go. Let's go through the Thevenin steps. Step 1. Determine VOC, which is the same as VTH. So here, 1 uses any method to calculate VOC. So when I look at the circuit, if I'm thinking voltages, so here's my circuit right here. So if I'm thinking voltages, let me add my A. I'm going to identify the nodes. So the first thing that I want to do is that I definitely want to put my ground right here. So when I look at this is clearly the ground node. So B is the ground node. This node right here is 18 volts. So I really have two nodes. I have this node and I have this other node right here. But we want the open here. So this right here is what we call VOC, which is the same as VTH. So this node becomes VOC, and for lack of a better name, I'm going to call this VX. So we want to calculate VOC. So if I do my counting, I could see here that without the ground, we have the red, the blue, and the green. So I have 3 nodes minus 1 source. So I have 2 nodes to solve for. So when I look at these 2 nodes, I have a node for VOC. I have a node for VX. So therefore, that gives me 2 equations, 2 unknowns for VOC and VX. So to me, there's lots of ways to solve this thing, but what I'm going to do is I'm going to apply node analysis. So I'm going to apply node analysis to determine VOC and VX. So let's do that. So if I focus on VX, or excuse me, VOC, I see that I have 2 resistors connected with 1 mutual with VX and 1 with 18. So writing that out, I'm going to say that the node VOC is then going to be 1/12, 1/10, and I'm going to get VOC. Then I have a mutual with VX. And then if I take the constant source of the 18 volts to the other side, I'm going to get 18 divided by 12. Now, let's focus on the node VX. So when I look at the node of VX, note that VOC is connected to VX only through the 10 ohm resistor. So then I'm going to write minus 10 VOC. And then I look at the node VX and there are 3 resistors. So I get 1/6, 1/3, 1/10 times VX. And then I still have to deal with the 18 volt source. There's a minus. I bring it over. It's going to be positive 18. And I'm going to divide that by 6. So now I have 2 equations and 2 unknowns. And so then again from matrix magic, I get that VOC and Vx now have values of 12 volts, and this is 7 volts. We only care about VOC. So what does this value mean again? I've said it a couple of times, but it's hard to comprehend what I'm actually saying here. Physically, what does VOC, which is the same as the Thevenin voltage, mean? And this only means from the viewpoint of the load. From the viewpoint of the load, the load does not see the full 18-volt source, but only a fraction of it. In the Thevenin circuit, again, from the viewpoint of the load, an observer will feel, maybe I should put quotes here, will feel an effective 12 volts, and no, I think that's good enough. Will feel an effective 12-volt source from the original circuit. So picture-wise, if I hope I still have a copy of it. Let me see if I do. Nope. I'm gonna cut that out. So I really need to take this guy right here. This is the one I really need right here. So I'm gonna copy this and I'm gonna bring it down with me. So picture-wise, this is what it looks like. I have to modify this just a tiny bit. So I keep saying from the viewpoint of the load. In other words, there is a 12-volt value between A and B. So if I look from the viewpoint of the load, so if you're standing right here, of course you don't see the 18 volts. You're seeing the 12 volts. In other words, the observer slash load feels a reduced voltage of 12 volts, not 18 volts. It's all from the viewpoint of the load. Okay, let's go to the second step now. So the second step, two here, we want to determine RTH. And there are two methods that we want to think about. So the first one that we're going to focus on is method 1, which is only valid for independent sources. Method 2 is valid for both independent and dependent sources. Method 1. Only valid for independent sources. So what we know here is that with the load removed, so what we know with the load removed, one deactivates all sources in the Thevenin, no, in the subcircuit. So if I let's see if I have that circuit. I don't have that circuit. I'm going to come here and I'm going to copy this circuit. So here's our circuit. So what we need to do is that now we need to deactivate that circuit. And so what happens here is that we need to now short out the voltage source. So if I look at that and I say the word deactivate, that means as I move from here to there, we deactivate the 18-volt source, which means I have to remove this from the circuit. And now I place a short. So now, from the viewpoint of the load, I'm now looking in between A and B as an observer, and I'm asking myself, what do I see from that viewpoint in terms of a resistance? So let's write this down. From the viewpoint of the load located at AB, there are only resistors left in the circuit. So at that point, we ask, what would this observer, which is also the load, experience resistively at this location? it would only feel a fraction of the total resistance in the circuit. It doesn't see all of the resistance. In other words, it feels an effect of resistance, and the word that really comes to mind here is like charge screening. What does a charge feel when it's outside the nucleus? There's charge screening, so it doesn't feel the full electric field of the nucleus, which we call the Thevenin resistance. So now we have this circuit. And the circuit that we have to do here is to solve for the Thevenin resistance. One uses reduction to compute RAB, which is the same as R Thevenin, or Norton for that matter. So if I stick in my circuit again, assuming I still have it, let me modify it. So this guy's not here anymore. So all we know is that between this point and that point, there's a short. And so we are only interested in R Thevenin from here. So if I look at the circuit, I could imagine that I send in and I place an ammeter. So place an ammeter at AB to read the resistance. So if I look at my circuit, this is what I'm seeing. Here's my circuit. So if I think about an ammeter, I can imagine that it goes something like this. I have an ammeter, and now it pumps in currents through node A, and the current comes out of node B. So if I rearrange this thing, I can redraw the circuit by now labeling nodes. So if I look at this node, my red node, and then I have one more node, nope, not one, but two. So when I look at this, I can redraw the circuit and it looks something like this. So I have a resistor, because I could see that the 10 ohm is in series with the 6 and the 3. So then I'm going to get 10 ohms. I'm going to have 3 here and 6. And then I see that the 12 is in parallel with everything. And so here's my 12 ohm. So then I have my nodes A and B. So if I look at my ohm meter again, here it is. Here's the current coming in here, and here's the current coming out. Again, coloring my nodes, here's my green node, the blue, and finally, my red node. So then, writing out the resistance of AB, we then see here that RAB is the same as RTH, and you could see here that I have a 12 ohm parallel to a combination of 10 plus in series with a 3 parallel to 6. So in other words, this will be 12 plus 10 plus 3 parallel to 6. And then this will be 12 parallel to a combination of 10 plus 3 parallel to 6. And when you compute this, you get a 6 ohm resistor. And this right here is the Thevenin resistance. Now we have everything. In other words, we now can calculate the details of the Thevenin equivalent. So here's my circuit. So I have a circuit, but of course we don't have that. What we have is an 18-volt source here. And this guy now looks like this. But if I now convert this into a Thevenin equivalent, I now have VTH, which is now 12 volts. I have a Thevenin resistance, which we now call 6 ohms. And this is AB. This is our Thevenin equivalent right here. That's what we were after, right there. So now let's make a couple of remarks and then move on to method 2. Remarks. One cannot tell the difference between the subcircuit on the left, and when I say left, I'm talking about this guy, from the Thevenin equivalent. And we gotta be careful here, right? We gotta be careful. From the viewpoint of the load. From the viewpoint of the load. So experimentally, and mathematically, these are identical. And I gotta be careful from the viewpoint of the load. 2. The Thevenin equivalent circuit is considerably easier to calculate the details of the load circuit. So picture-wise, if I have this circuit and now I place a load right here. This circuit, from the viewpoint of the load, can then be replaced with this guy right here. So if I'm looking to calculate the current or the voltage of the load, you got to admit that this is more challenging. This is much less challenging.